The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay. I hoped I might have those exam 2 for you today, but it's not quite back from the grader. It's already gone to the second grader, so it will not be long. I hope you've had a look at the MATLAB homework for Friday, if possible. I think we've got there were some errors in the original statement location of the coordinates, but I think they're fixed now. So ready to go on that MATLAB. Don't forget that it's 4 on the right-hand side and not 1. So if you get an answer near 1/4 at the center of the circle, that's the reason. Just that factor 4 is to remember. I'll talk more about the MATLAB this afternoon in the review session right here. Just to say, I'm highly interested in that problem, not just increasing n, the number of mesh points in the octagon, but also increasing the number of sides. So, so there are two numbers there. N, we had n points on a ray out from the center, but we have m sides of the polygon, and I'm interested in both of those getting big, growing. I don't know how, and maybe a reasonable balance is to take, I think n proportional to m is a pretty good balance. So I'd be very happy. I mean, I'm very happy with whatever you do, but I'm really interested to know what happens as both of these increase. How quickly do you approach the eigenvalues of a circle? And you might keep the two proportional as you increase them. So let me say more about that this afternoon, because it's a big day today to start Fourier Series, the new chapter, the new topic, in fact, the final major topic of the course. So I tried to list here, so here I'm in section 4.1, so I'm talking about Fourier series. So Fourier series is for functions that have period 2 pi. It involves things like sine x, like cosine x, like e to the I kx. All of those, if I increase x by 2 pi, I'm back where I started. So that's the sort of functions that have Fourier series. Then we'll go on to the other two big forms, crucial forms of the Fourier world. But 4.1 starts with the classical Fourier series. So I realize you will have seen, many of you will have seen Fourier series before. I hope you'll see some new aspects here. So let me just get organized. I kind of, it's nice to have some examples that just involve signs. And since the sine is an odd function, that means it's sort of anti-symmetric across 0, those are the functions that will have only sine, that will have a sine expansion. Cosines are the opposite. Cosines are symmetric across 0, like a constant or like cosine x. 0 comes right at the symmetric point. So those will have only cosines. And a lot of examples fit in one or the other of those, and it's easy to see them. The general function, of course, is a combination, odd and even. It has cosines and it has sines. It's just the sum of the two pieces. So this is the standard Fourier series, which I couldn't get onto one line, but it has all the cosines, including this slightly different cosine of 0, and all the sines. But because this one has these three different pieces, the constant term, the other cosines, all the sines, three slightly different formulas. It's actually nicest of all to use this final form, because there's just one formula, there's just one kind, and I'll call its coefficient ck, and now they multiply e to the ikx, so we have to get used to e to the ikx. We may be more familiar with sine kx and cos kx, but everybody knows e to the ikx is a combination of them. And if we let k go from minus infinity to infinity, so we've got all the terms, including e to the minus I 3x and e to the plus I 3x, those would combine to give cosines and sines of 3x. We get one nice formula. There's just one formula for the c's. So that's one good reason to look at the complex form, even if our function is actually real. That form is kind of neat. And the second good reason, the really important reason, is that when we go to the discrete Fourier transform, the DFT, everybody writes that with complex numbers. So it's good to see complex numbers first, and then we can just like translate the formulas from, and these are also almost always written with complex numbers. So this is the way to see it. Okay. So what do we do about Fourier series? What do we have to know how to do, and what should we understand? Well, if you've met Fourier series, you may have met the formula for these coefficients, right? That's sort of like step one. If I'm given the function, whatever the function might be a delta function. Interesting case, always interesting. Always crazy, right? But it's always interesting, the delta function. The coefficients can be computed. The coefficients, you'll see, I'll repeat those formulas. They involve integrals. Well, what I want to say right now is that this isn't a course in integration. So I'm not interested in doing more and more complicated integrals and finding Fourier coefficients of weird functions. No way. I want to understand the simple, straight, the important examples. And here's a point that's highly interesting in practice, in computing practice. We're close to computing practice here in everything we do. I mean, this is really constantly used. And one important question is the Fourier series quickly converging? Because if we're going to compute, we don't want to compute 1,000 terms. You know, hopefully 10 terms, 20 terms would give us good accuracy. So that question comes down to, how quickly do those A's and B's and C's go to 0? That's highly important. And you'll connect this decay rate, we'll connect this with the smoothness of the function. Oh, I can tell you even at a start here. Okay, so I just want to emphasize this point. We'll see, and we'll just see it over and over, that like for a delta function, which is not smooth at all, we'll see no decay at all in the coefficients. They're constant. They don't decrease as we go to higher and higher frequencies. I think of k here, I'll use the word frequency for k. So high frequency means high k, far out the Fourier series. And the question is, are the coefficients staying up there big and we have to worry about them, or do they get very small? So a delta function is a key example, and then a step function. So what will be the deal with those? If I have a function that's a step function, I'll have decay rate is 1 over k. So they do go to 0. The 1,000th coefficient will be roughly of size 1 over 1,000. That's not fast. That's not really fast enough to compute with. So we're not, well, we meet step functions, but I mean functions with jumps, and we'll see that their Fourier series do go, the coefficients do go to 0, but not very fast, and we get something highly interesting. So when we do these examples, so I've sort of moved on to examples. So these are two basic examples. What would be the next example? Step function? Yeah, or maybe a hat next. A hat function would be, you see what I'm doing at each step, I'm integrating. A hat function might be the next. Yeah, a ramp, exactly. Hat function, which is a ramp with a corner. Now, so that's one integral better. You want to guess the decay rate on that one? K squared. Now we're getting better. We can, that's a faster fall off. 1 over K squared. And then if we integrate again, we'd get 1 over K cubed. If we went, then one more integral, 1 over K fourth would be a cubic spline with, you remember the cubic spline is continuous. Its derivative is continuous. That gives us a 1 over K cubed. Its second derivative is continuous. That gives us a 1 over K to the fourth. And then you really can compute with that if you have such a function. So pay attention to decay rate. And the connection to smoothness. That will be, so examples is, we'll start right off with these guys. And then we'll see the rules for the derivative. Oh yeah, rules for the derivative. The beauty of Fourier series is, of course, well, actually, you can see this. You can see the rule. Let me just show you the rule for this. So the rule for derivative, the whole point about Fourier is it connects perfectly with calculus, with taking derivatives. So suppose I have f of x equals, I'll use this form, the sum of c k e to the I kx. And now I take its derivative, df dx. What do you think is the derivative? What's the Fourier series for the derivative? If I suppose I have the Fourier series for some function, and then I take the Fourier series for the derivative. So I'm kind of going the backwards way, less smooth. I'm going from the derivative of the step function involves delta function. So I'm going less smooth as I take derivatives. Well, it's so easy to, it jumps at you. What's the rule? Just take the derivative of every term. So I'll have the sum of, now what happens when I take the derivative? Everybody see what happened when I take the derivative of that typical term in the Fourier series? What happens? The derivative brings down a factor ik, k being the thing that, so it's ik times what we had. So these are the Fourier coefficients of the derivative. And that again makes exactly the same point about the decay rate, or the opposite, the non-decay rate. As I take the derivative, you get a rougher function, right? Derivative of a step function is a delta. Derivative of a hat would have some steps. We're going less smooth as we take more derivatives. And every time we do it, we see, you understand the decay rate now, because the derivative just brings down a factor ik. So its high frequencies are more present, have larger coefficients. Yeah, so, and of course, the second derivative would bring down ik squared. So that our equations for example, let me just do an application here without pushing it. Our application, we started this course with equations like minus u double prime of x equal delta of x minus a. Right? that if we wanted to apply to a differential equation, how would I do it? I would take the Fourier series of both sides. I would I'd jump into what people would call the frequency domain. So this is a differential equation written as usual in the physical domain, with physical variable x, position, or it could be time. And now let me take Fourier transforms. So what would happen here? If I take the Fourier transform of this, well, we'll soon see, right? We get Fourier coefficients of the deltas, of the delta function. That's a key example, and you see why. Over here, what will we get? Now I'm taking two derivatives, so I bring down ik twice. So I'm looking, here it would be the sum of the delta, whatever the delta's coefficients are. Should we call those d? How? The alphabet's coming out right here. D for delta. So the right side has coefficients dk. And what about the left side? What are the coefficients? If the solution u has coefficients ck, so let's call this u now, has coefficients ck, then what happens to the second derivative? ik again, that's I squared k squared, the minus sign, so we would have the sum of k squared ck e to the ikx. This is if u itself has coefficients ck, then minus u double prime has these coefficients. So what's up? How would we use that? It's going to be easy. We'll just match terms, right? I can see what's my formula, what should ck be if I know the dk, right? I'm given the right-hand side. We're just doing what's constantly happening, this three-step process. You're given the right side. Step one, expand it in Fourier series now. Step two, match the two sides. So what's the formula for ck in this application, which by the way, I had no intention to do this, but it jumped in my head and I thought, why not just do it? What would be the formula for ck? It'll be dk divided by k squared. You're just matching terms. Just the way when we expanded things in eigenvectors, we matched the coefficients of the eigenvectors, and that involved just this simple step, like here, it's dk over k squared. Good. And then what's the final step? The final step is, now you know the right coefficients, add them back up, add the thing back up, like here, only I'm calling it, I'm temporarily calling it u, to find the solution, right? Three steps. Go into the frequency domain. Write the right-hand side as a Fourier series. Second quick step is look at the equation for each separate Fourier coefficient. Match the coefficients of these eigenvectors, eigenfunctions. And that's this quick middle step. And then you've got the answer, but you're still in Fourier space, you're still in frequency space. So you have to use these, put them back to get the answer in physical space, right? That's the pattern, over and over. So that's sort of the general plan of applying Fourier. And when does it work? When does it work? Because, I mean, it's fantastic when it works. So what is it about this problem that made it work? When is Fourier happy? You know, when does he raise his hand and say, yes, I can solve that problem? Okay, what do I need here for this plan to work? I certainly don't need always just minus u double prime. Fourier could do better than that. But what's the requirement for Fourier to work perfectly? Well, linear equation, right? If we didn't have linear equations, we couldn't do all this adding and matching and stuff. So linear equations, well, okay. What other linear equations? Could I have a C of x in here? My familiar C of x, variable material property, inside this equation? No. Well, not easily anyway. That would really mess things up. If there's a variable coefficient in here, then it's going to have its own Fourier series. We're going to be multiplying Fourier series. That comes later, and it's not so clean. So it works perfectly when it's constant coefficients. Constant coefficients in the differential equation. And then one more thing. Very important other thing. The boundary conditions. Everybody remembers now. It's a part of the message of this course is that boundary conditions are often a source of trouble. They're part of the problem. You have to deal with them. Now, what boundary conditions do we think about here? Well, fixed was where we started. So if we had fixed boundary conditions, what would I expect? Then things would give me a sine series, possibly. Yeah, right, because those are the eigenfunctions we're used to. Fixed. It's sines that go from 0 back to 0. Fixed free will have some sines or cosines. Periodic would be the best of all. Yeah, so we need nice boundary conditions. I don't know. So the boundary conditions, let me just say, periodic would be great, or we can sometimes fix free. Our familiar ones, at least in simple cases, can be dealt with. Right. Okay. So now, boy, that board is already full of formulas. But let's go back to the start and say, how do we find the coefficients? Okay. So because that was the first step. Take the right-hand side, find its coefficients. If we want to, just as the applying eigenvalues, the first step is always find the eigenvalues. Here, in applying Fourier, the first step is always find the coefficients. So how do we do that? And at the beginning, it doesn't look too easy, right? Because let me take the first guy, sine x. Let me take an example. A particular s of x. The most important, interesting function, s of x. I want it to be an odd function so that it will have only sines. So let me just graph, and I should have period 2 pi. So let me just graph it. Here it'll be, so it's going to have coefficients, and I use b for sines. So it's going to have b1 sine x and b2 sine 2x and so on. So it's got a whole infinity of coefficients. Right? We're in function space. We're not dealing with vectors now. So we've got, how is it possible to find those coefficients? And let me chose a particular s of x. So I'll put it, since it's 2 pi periodic, if I tell you what it is over a 2 pi interval, just repeat. So I'll pick the 2 pi interval to be minus pi to pi here, just because it's a nice way. And so that's a 2 pi length. There's 0. I want the function to be odd across 0. And I want it to be simple, because it's going to be an important example that I can actually compute. So I'm going to make it a 1 there, and a minus 1 there. So a step function. A square. And if I repeat it, of course, it would go down, up, so on. But we only have to look over this part. Okay. Now, well, you might say, wait a minute, how are we going to expand this function in sines? Well, I mean, sines are odd functions. Everybody knows what odd means. Odd means that s of minus x is minus s of x. So that's the anti-symmetric that we see in that graph. We also see a few problems in this graph. The sign at x equals 0, what is our sign series going to give us? If I plug in x equals 0 on the right-hand side, I get 0, certainly. So the sign series is going to do that. And actually, Fourier series tend to do this. In the middle of a jump, it'll pick the middle point of a jump. Fourier series, generally, it's the best possible, will pick the middle point of the jump. And what about at x equal pi, at the end of the interval? What does my series add up to at x equal pi? 0 again, because sine of pi, sine of 2 pi, all 0. So it'll be, and that'll be in the middle of that jump. So it's pretty good. Yep. But now what I'm hoping is that my sine series is going to somehow get real fast up to 1 and level out at 1. We're asking a lot. And in fact, when Fourier proposed this idea of Fourier series, there was a lot of doubters. Was it really possible to represent other functions, maybe even including a step function, in terms of sines or maybe cosines? I mean, and Fourier said, yes, go with it. So let's do it. Okay, so, and he turned out to be incredibly right. Yeah, I mean, he just, okay, how do I find B2? Do you remember how to, I don't want to know the formula. I want to know why. What's the step to find the coefficient B2? Well, the step is the key point, and which makes everything possible. Why don't I identify the key point without which we would be in real trouble? The key point is that all these sine functions, all this sine 2x, sine 3x, sine 4x are orthogonal. Now, what do I mean by two functions being orthogonal? Somehow, my picture in function space, so my picture in function space is that here's, this is the sine x coordinate, and somewhere there's a sine 2x coordinate, and it's 90 degrees, and then there's a sine 3x coordinate, and then there's a sine, I don't know where to point now, but there is a sine 4x, and we're in infinite dimensions, and the sine vectors are an orthogonal basis. They're orthogonal to each other. What does that mean? Vectors, we take the dot product. Functions, we don't use the word dot product as much as inner product. So let me take the inner product of, the whole point is orthogonality. Let me write that word down. Orthogonal. The signs are orthogonal. And what does that mean? That means that the integral over our 2 pi interval, or any 2 pi interval, of one sine kx, let's say, multiplied by another sine lx dx is, you can guess the answer, and it's everything, everything is depending on this answer, and it is 0. It's just terrific, right? If k is different from L, of course. If k is equal to L, then I have to figure that one out. I'll need that one. What is it if sine, if k equals L, so I'm integrating sine squared of kx, then it's certainly not 0. I'm getting like the length squared of the sine kx function. If k equals L, what is it? It has some nice formula. Very nice. Let's see. Sine squared, do I need to think about sine squared kx? Sine squared kx, what does it do? Well, just graph sine squared x. What would the graph of sine squared x look like from minus pi to pi? So it goes up right? Doesn't it go up? And then it goes back down. Okay. Sorry, I made that a little hard. Is that right? And then it keeps it up. Right. So what's the integral of that? I'm not seeing quite why. The answer is its average value is a half. The integral of sine squared is half of the length. The whole interval is of length. This is length 2 pi. And we're taking the area under sine squared. I may have to come back to it, but the answer will be half of 2 pi, which is pi. Yeah, yeah. So the length, you could say, the length of the sine function is square root of pi, sort of, right? Yeah. So these are integrals. You told me the answer was 0, and I agreed with you, but we haven't computed it, and nor have we really got that one. So a little bit to fix still, but the crucial fact, I mean, these are just, I won't say just, those are highly important integrals that just come out beautifully. And beautifully really means 0. I mean, that's the beautiful number, right, for an integral. Okay, so now how do I use that? Again, I'm looking for B2. How do I pick off B2? Using the fact that sine 2x times any other sine integrated to 0. Ready for the moment to find the coefficient B2? Let me start the sentence, and if you finish it, I'll multiply both sides of this equation by sine 2x, and then I will, what? Integrate, right. I'll multiply both sides by sine 2x, so I take s of x, sine 2x, and on the right hand I have b1 sine x, sine 2x, and then I have b2. Now here's the one that's going to live through the integration. It's going to survive because it's the sine 2x times sine 2x, sine 2x squared. And then comes the B3 guy, would be B3 sine 3x sine 2x. You see everybody sees what I'm doing? It's as we did with the weak form in differential equations. I'm multiplying through by these guys, and then I'm integrating over the interval. And what do I get? Integrate every one dx, and what's the result? What is that integral? 0. It's gone. What is this integral? The integral of sine 3x times sine 2x. 0. All those signs are integrate to 0, and I have to come back and see it's a simple trig identity to do it, to see why that's 0. Do you see that everything is disappearing except B2? So we finally have the formula that we want. Let me just put these formulas down. So BK, B2 or BK, yeah, tell me the formula for BK. Let me go back here. What did B2 come out to be? So I have B2, that's a number. It's got this right-hand side. That's the integral that I mentioned, that you'd have to compute that integral. And then what about this stuff? This sine of 2x squared. I've integrated that. And what did I get for that? That was, yeah, this is B2, and then this is some number, and it's pi. So this is B2 and multiplying, right? That B2 comes out, and then I have the integral of sine squared 2x, and that's what's pi. So that's B2 times pi here, and I just divide by the pi. So I divide by pi, and I get the integral from minus pi to pi of my function times my sine that's the model for all the coefficients of orthogonal series. That's the model, the cosines, the complete ones, the complex coefficients, the Fourier, the Legendre series, the Bessel series. Everybody's series will follow this same model because all those series are series of orthogonal functions. Everything is hinging on this orthogonality, the fact that one term times another gives 0. What that means, really, I always want to say it with a picture, too. What does it mean that so let me draw 2 orthogonal directions. I won't make them, I intentionally didn't make them just x and y axes. This might be the direction of sine x, and this might be the direction of sine 2x. And then I have a function. And I'm trying to find out how much of sine 2x has it got in it, how much of sine x has it got in it, and then, of course, there's also a sine 3x and all the other sine kx's. The point is, the point of this 90-degree angle there is that if I can split this s of x, whatever it might be, I can find its sine x piece directly by just projecting it. It's the projection of my function on that coordinate. If you don't like sine x, sine 2x, s of x, write v1, v2, whatever, to think of it as vectors. What's the sine 2? So that is b1 sine x. That's that's the right amount of sine x. And the whole point is that calculation I did not have to do, it didn't involve b2 and b3 and all the other b's. When I'm projecting onto orthogonal directions, I can do them one at a time. I can do one-dimensional projection at a time. This bk, to say it, bk sine kx is so I'm just saying this in words, is the projection of my function onto sine kx. And the point is, I could do this and get this answer because of that 90-degree angle. If I didn't have 90 degrees, do you see that this wouldn't work? Suppose my 2 basis functions are at some 40-degree angle. Then I take my function. Can I project that onto this guy and project that onto this guy so the projections are there and there? Do they add back to the function that I started with, the given function? No way. I mean, these are much too big, right? If I add that one to this one, I'm way out here somewhere. But over here, with 90 degrees, these are the 2 projections. Project there, add those 2 pieces, and I got back exactly. I just want to emphasize the importance of orthogonality. It breaks the problem down into one-dimensional projections. Okay, so here we go with bk sine kx. Okay, let me do the key example now. This example. Let me find the coefficients of that particular function s of x. This is the step function, the square wave s of x. Let's find its coefficients. I'll just use this formula. Okay. Maybe I'll erase so that I can write the integration right underneath. Okay. Oh, one little point here. Well, not so little, but it's a saving. It's worth noticing. It's the reward for picking off the odd function is, I think that this integral is the same from minus pi to 0 as 0 to pi. In other words, I think that for an odd function, I get the same answer if I just do the integral from 0 to pi of my that I have to do, and double it. So I think if I just double it, that's I don't know if you regard that as a saving. In some way, the work is only half as much. It'll make this particular example easy. So let me do this example. What are the Fourier coefficients of the square wave? Okay, so I'll do this integral. So from 0 to pi, what is my function from the graph? It's just 1. This is going to be a picnic, right? The function is 1 here. So s of x is 1, so I want 2 over pi, the integral from 0 to pi of just sine kx dx, right? Which is, so I've got 2 over pi. Now I integrate sine kx, I get minus cosine kx, right? Between 0 and pi. And what else? What have I forgotten? Most important point. The integral of sine kx is not minus cosine kx. I have to divide by k. It's that division by k that's going to give me the correct decay rate. 2 over pi k. All right, now I've got a little calculation to do. I have to figure out what is cosine kx. At 0, no problem, it's 1. And at the other point, at x equal pi. So what am I getting then? I'm getting 2 over pi. And this one is, no, 2 over pi k. All important, pi k. With that minus sign, I'll evaluate it at x equals 0. I have 1 minus whatever I get at the top, cosine of k pi. That's bk. So there's a typical, well, not typical, but very nice answer. Now let's see what these numbers are. So let me take a 2 over pi out here. And then just list these numbers. At k equal to, so k is 1, 2, 3, 4, 5, right? Just tell me what these numbers are for, let me put the k in here, because that's part of the, so there's a constant, 2 over pi. What is, at k equal 1, what do I get? At k equal 1. This is now, this is the little bit that needs the patience. At k equal 1, the cosine of pi is -1. So I have minus 1. I get a 2. I get a 2 over a 1. K is 1. All right, this is the coefficient for k equal 1. Now what's b2, the coefficient for k equal 2? I have 1 minus cosine of 2 pi. What's cosine of 2 pi? 1. So they cancel, so I get a 0. There is no b2. What about b3? So now b3, I have 1 minus the cosine of 3 pi. What's the cosine of 3 pi? It's -1 again, right? Same as the cosine of pi. So that gives me a 2, and now I'm dividing by 3, 2 over 3. All right, let's do 2 more. K equal 4, what do I get? 0, because the cosine of 4 pi has come back to 1. So I get a 0. And what do I get from k equal 5? 1 minus the cosine of 5 pi, which is back to, cosine of 5 pi is back to -1. So 1 minus -1 is a 2. You see the pattern. And so let me just copy the famous series for this s of x. This s of x is, let's see, the 2's, I'll make the 4 over pi, right? I'll take out all those 2's. So I have 4 over pi sine x. I have no sine 2x, forget that. Now, I do have some sine 3x's. How much do I have? 4 over pi sine 3x's. What's the, but divide by 3, right? And then there's no 4x's, no sine 4x's. But then there will be a 4 over pi sine, what's the next term now? Are you with me? So this is a typical, nice example, important example. Sine of what? 5x divided by 5. Okay. That's a great example. It's worth remembering. Factor the 4 over pi out if you want to. 4 over pi times sine x, sine 3x over 3, sine 5x over 5. It's a beautiful example of an odd function. Okay. And let's see. So what do you think? MATLAB can draw this graph far better than we can, but let me draw enough so you see what's really interesting here. It's famous, interesting and famous. So the leading term is 4 over pi sine x. That would be something like that. That's as close as sine x can get. 4 over pi is the optimal number, the optimal coefficient, the projection. This 4 over pi sine x is the best, the closest I can get to 1 on that interval. And now, but with just sine x. But now when I put in sine 3x, I think it'll do something more like this. Do you see what's happening there? That's what I get with sine 3x, and of course odd on the other side. What do you think it looks like with sine 5x? You really have to, it's just so great, you have to let the computer draw it a couple of times. You see, it goes up here, and then it's sort of, you know, it's getting closer. It's going to stay closer to that, but I don't know if you can see from my picture. I'm actually proud of that picture. It's not as bad as usual. And it makes the crucial point that, 2 crucial points. One is, I am going to get closer and closer to 1. These oscillations, these ripples, will be smaller. But, here's the great fact, and it's a big headache in calculation. At the jump, the first ripple doesn't get smaller. The first ripple gets thinner. The first ripple gets thinner. You see the ripples moving over there, but their height doesn't change. Do you know whose name is associated with that phenomenon? Gibbs. Gibbs noticed that the ripple height, as you add more and more terms, you're closer and closer to the function over more and more of the interval. But so the ripples get squeezed to the left. The area under the ripples goes to 0, certainly. But the height of the ripples doesn't. And it doesn't stay constant, but nearly constant. It approaches a famous number. And of course, we'll have the same odd picture down here. So, and it'll bump up again. It's the same thing is happening at every jump. In other words, if you're computing shocks, if you're computing airflow around shocks with Fourier-type methods, Gibbs is going to get you. You will have to deal with Gibbs because the shock is not, the shock has that extra ripple. Okay, that's a lot of section 4.1. Energy we didn't get to, so that'll be the first point on Friday. And I'll see you this afternoon and talk about the MATLAB or anything else. Okay.